symmetrical three-phase system. Symmetrical three-phase system. Consider a electrical system, three-phase system as shown in the figure. The phases are identical in magnitude, that is in RMS, but the phases are displaced by 120-degree apart. So already we have seen the phasor diagram, 120-degree apart from each other, as shown in the figure 7.3. The phase sequence is A, B, C. So you see this three-phase system. This is the simple three-phase system having the generator of VA, VB, VC, and having the impedance of ZG, that is generator impedance of first A phase ZG impedance. Next, having the current of IA, okay, that is this transmission line having the current of IA, and here load impedance having Z. Similarly, the phase B having the voltage VB. Okay, so here you see the sequence. Okay, the sequence here it is positive, here it is negative VA. So VB here it is positive, here it is positive. So VC here it is positive, here it is negative. Okay, so this is the polarities of this particular generator that is converted into single line diagram, and having the impedance ZC, IC, Z, and here it is neutral. Neutral, we are having IN. So this is the load, neutral load, and here generator neutral. Okay, so this is a simple three-phase electric system. And here you see the phases are identical in magnitude, that is RMS, but displaced by 120-degree apart. So you see here, this is the three-phase phasor diagram, BA, BB, BC, having the displacement 120-degree apart. This already we have seen in our basic classes, how 120-degree apart and all. So I don't want to discuss in detail. Next comes the voltage relations. Voltage relations. Generated terminal voltage is equal to EMF generated minus voltage drop. So what is that generated terminal voltage? Generated terminal voltage is nothing but EMF generated minus the voltage drop. There is definitely some voltage drop will be there. That voltage drop also we need to minus. So that gives the terminal voltage of the generator. So because of the symmetry, terminal voltage will like EMFs having the relative time phase. The terminal voltage will like EMF having the relative time phase. Phase to neutral voltage of the phases A, B, and C can be rewritten as VA into √2 VP sine omega t, where V RMS equal to VP divided by √2, VP divided by √2. So in terms of what you call V RMS equal to VP divided by √2. So V peak, in terms of V peak, so you need to multiply with √2. So VA is equal to √2 into VP sine omega t. Similarly, VB is equal to √2 into VP sine omega t minus 120. Here VC is equal to √2 into VP sine of omega t minus 240. This you know how minus 120 with that phasor diagram, minus 120 minus 240 like that. So this √2 into VP sine omega t minus 240 is nothing but sine omega t plus 120. So you may tell minus 240 or plus 120, where VP is nothing but phase voltage measured in RMS, root mean square. Root mean square. These are next. Let the reference voltage between the VA can be rewrite as VA, VB, and VC. That is, VA is equal to VP at the angle of 0 degree. VB is equal to VP at the angle of minus 120 degree. VC is equal to VP at the angle of minus 240 degree. That is nothing but VP at the angle of 120 degree. Let VAB, VBC, and VCA be the line voltages. So we can rewrite we can write this line voltage in terms of phase voltages, that is VAB, that is line voltage is equal to VA minus VB, VBC is equal to VB minus VC, VCA is equal to VC minus VA. Next comes the magnitudes of the line voltage. So voltage and current phasors in symmetrical three-phase systems are shown in the figure. So symmetrical three-phase system, that is voltage and the current phasors in symmetrical three-phase system. That is, you are having voltage at a phase A is equal to VA, and voltage at the phase C is equal to VC, and the voltage at the phase B is equal to VB. So this is 120 degree. This is also 120 degree. This is also 120 degree. So here you see this is also 120 degree. So this side IC IC to B, sorry, not IC, VC to VB. So this also 120 degree. This also 120 degree. And again, this also 120 degree. This also 120 degree. That we have seen. So this phase angles. And here you see the current IA. Okay, so we'll have the angle of phi. Okay, between VA and IB. You are having an angle of this also pi. This also some phi will be there. And here also this angle if you take this also some phi. Okay, between IB and VB. So this angle, what is this angle? We need to derive that, we'll see. Okay, so here if you say this is the VA, say for example this is the VB. So VB in the negative direction, this you can call it as, I think, yeah, I'm drawing neatly so that you can understand. So this, yeah, this VB in terms of, okay, in terms of this angle, say for example, this is VB in terms of minus, say for example, minus VB in terms of this particular okay, direction. So this also VB, no, the same thing here also VB will come. So if you take so if this is 120, okay, between VA and this VC is 120, this is off. So this is 60. Say for example, this is 60. This is 60 degree because total is 120. This is 60. So what is the resultant? Resultant is VAB. VAB is the resultant. VAB is the resultant like this. Okay, so I wrongly drawn like this. So if you exactly draw like this, you'll get equal distance between these two. Okay, so while you drawing, you draw equal. So this the resultant is VAB. So VAB. So that's what here they have given. So resultant is VAB. So VA cos the 30 degree. VA cos 30 degrees equal to VP. VP means V peak. So cos 30 √3 divided by 2. That you know. Next, coming to the equations. Yeah, line voltage equal to VAB is equal to VBC is equal to VCA. So that is nothing but 2 into VA. Okay, 2 into VA. So what is this VA? VA is nothing but phase voltage. So as I said, in terms of phase voltage, we need to rewrite this line voltage. 2 into VA into cos 30. Cos 30 what? √3 divided by 2. This 2 and 2 get cancelled. This 2 and 2 get cancelled. So √3 into VP. So VA in terms of VP. So in the VP we are writing. So VL line voltage in symmetrical three-phase system, line voltage is equal to √3 into VP. √3 into VP. So that √3 is there. This VP is there. So VL is nothing but line voltage and VP is nothing but phase voltage. That is what here. So here VA is cos 30 is equal to VP into √3 by 2. So VA in terms of VP into √3 by 2. This is the voltage and current phasors in the symmetrical three-phase system. Already I explained how it is coming. Like the same thing here also they explain. So I explained this phase. They have explained this phase. That's all. Okay. And according to power triangle, this we are writing V into cos 30 degree like that. We are writing. Next comes the current relations. What is the current relation? If the load is assumed balanced on and symmetrical, then three-phase currents are. Okay, three-phase currents are similarly. We have seen now how this √2 comes. So IA is equal to √2 into IP. Okay, IP that is in terms of this RMS. Okay, in terms of RMS, √2 into IP sine of root omega t minus phi. Omega t minus phi. This is the IA. So IB is equal to √2 into IP sine of omega t minus phi minus 120 degree. Next IC is equal to √2 into IP into sine of omega t minus phi minus 240 degree. Let the reference phase current be IA, that is IA lags VA by an angle of phi. As I said before, IA lags the angle of VA by phi. So here, if you see IA, say this is IA lags the lagging the VA with the angle of phi. So that's what they also said here. By Fi, we can rewrite this equation as, so IA is equal to I peak at the angle of minus phi, IB is equal to IP at the angle of minus phi minus 120 degree, IC is equal to IP at the angle of minus phi minus 240 degree. So here IP is equal to minus phi plus 120 degree in terms of minus 240 plus 120 degree. In star connected system, the line currents are equals to the phase currents, that is IL is equal to IP. Then the net current IN, the neutral, is the sum of the three phases, that is IN is equal to IA plus IB plus IC. In three-phase symmetrical or balanced system, IN is equal to IA plus IB plus IC, that is equal to 0. All phase voltages can be measured relative to the system ground, which has same potential 0 throughout the whole system. All the phase voltage that is measured relative to the system ground, which has same potential 0 throughout the whole system. That is IN is equal to IA plus IB plus IC is equal to 0. Then comes to the power relation. Power relation, how? The total transmitted instantaneous three-phase power is equal to the sum of the individual phase powers that you know. V three-phase equal to VA IA plus VB IB plus VC IC. By substituting the instantaneous values of voltage and current, we can rewrite this as 3 into VP IP cos phi. This already we have seen. So how we need to write in terms of instantaneous values. Okay, so the same equation can be rewritten as 3 into VP IP cos phi. 3, so it's nothing but 3 into V single phase. Okay, that is three-phase power is equal to 3 into single phase power. That is what said here in watts, where P one phase is equal to single phase power. Next, three-phase reactive power. Similarly, three-phase reactive power is equal to 3 into Vp into sine phi p. So sine phi p in terms of complex power. So we can rewrite this as 3 into Q single phase. That is in VAR. 3 into Q single phase. That is in VAR. Next, three-phase apparent power. That is S three-phase equal to 3 into S single phase. Apparent power, you may represent apparent power as S. Okay, so apparent power as S. So S into single phase, that is equal to 3 into Vp into Ip in terms of VA. So here, similarly, reactive power of three phase equal to 3 into reactive power of single phase. Here, three phase apparent power is equal to 3 into Vp IP. That is in VA.